Recordings. All right, so now the recording is going as well. The topic, of course, is global climate change. And I'm going to focus a little bit, I guess, on a few issues that I feel like the research I'm doing right now is helping me to understand better and to share what I'm learning with you. I'm going to focus in the first instance on extreme weather. And this is, in a sense, one of the more superficial aspects of climate change. It's not what is ultimately going to threaten biological life on the planet. That is going to be the heating of the planet and the disruption of the eco or earth systems that stabilize and maintain the planet in a temperate zone that facilitates biological life thriving on the planet. But having said that, extreme weather is the aspect of climate change that most directly and immediately impacts human beings in 2022. And the summer of 2022 may be the summer of extreme weather. Obviously, I suspect we can anticipate that this will get worse year after year, but this seems like the summer in which, in many places on the planet, people are simultaneously coping with the consequences of extreme weather in a way that I think is making it increasingly irresistible to not feel the impact of climate change. And then I'm going to look at some of the science, the new methods for understanding the threat that human beings are posing for the planet as a whole, and then some of the questions about the cultural resources. And so I'm using a couple phrases in my title that are borrowed from some of the stuff I'm reading. The Great Derangement is the title of Amitav Ghosh's book on the limits of the human imagination as it has been shaped by Western high intellectual culture to grasp climate change, to make sense of it, to understand the depth of the threat that our disruption of planetary ecosystems and ultimately of the climate represents to us. The other phrase, and I imagine some of you may recognize this, the Ministry of the Future, is a work in science fiction by Kim Stanley Robinson, a well-known contemporary science fiction writer, author, among other things, of the Mars trilogy, which is, I think, quite well known. The Ministry of the Future is, on the one hand, a novel that tries to help us to gain, if you will, the imaginary traction, to make sense of what is coming. And so that novel begins by imagining a heat wave that hits northern India that kills 20 million people, right? So a genuine Holocaust. It imagines this occurring this decade, right? So this is not a distant future dystopian novel. This is a science fiction reconstruction of more or less the present. And it tells the tale of that humanitarian disaster from the first person perspective of the lone survivor. And for those of you who might be interested in reading this, I promise you I'm not spoiling it. This is just the opening setup for the novel. But I have to say it was very hard to read. And it was hard in a good way, in the sense that it made the reader really think through what it might be like to live at a time where the weather overwhelmed the civilizational resources that we have, the capacity we have to cool our air with air conditioning, to take care of ourselves with all the infrastructure that we've built, and that ultimately everything that we've done to protect ourselves from nature is going to be totally insufficient if the nature of the future is different from the nature of the past. We have evolved our culture, but also our physical infrastructure in a climate that we are leaving behind. Can we develop the cultural resources to stop ourselves from doing further damage to it before it's too late? Right. And so I hope that kind of scattershot set of questions makes sense as having some internal cohesion. Let me get into the basic ideas here. The summer of 2022, right? Dangerous heat waves spreading through the United States, not just the West, or not even primarily the West, in July, right? France and Spain on fire. Britain, it's by far and away hottest weather conditions ever detected. And then, right, we look at Europe as a whole, still in the grips of the worst drought, people say, in probably 500 years, right? We had the terrible floods in Kentucky, but even worse have been the monsoon rains in Pakistan just this last week, flooding that almost certainly has killed thousands of people. We have this tremendous drought, again, perhaps 500 or even 1,000-year drought gripping China. Among other things to notice is that the Chinese are shutting down factories in some of their most important industrial productive regions in order to be able to conserve electricity for air conditioning and other essential needs. And of course, we're in a moment where the world is experiencing inflation, and Chinese factories being shuttered in order to conserve electricity for civilian uses is not good for the world economy, but it's essential to the survival of the people of China as they experience extreme weather and drought conditions. And I could keep going with the illustrations here, but I think that the thing to note is that the trend line is unmistakable here, right? And so we look at the recent global temperature records, right? And this does not go up to 2021, but 2020 was the warmest year on record. 2019, the third. 2018, the sixth. 2017, the fourth. 2016, the second. 2015, the fifth warmest year in history. And we can be pretty confident our ice cores, our tree rings, including fossilized tree rings, our sediment from the deep oceans allow us to reconstruct weather patterns, temperatures going back now nearly 1 million years. And all of this heat is concentrated in the most recent 20 years. And by the way, though the summer of 2020 is bad, I'm sorry, 2022, 2020, another European heat wave killed thousands. Extreme flooding in Bangladesh killed thousands. The Australian wildfires did tremendous damage to the natural environment of Australia. Siberia's record heat wave in the summer of 2020, which did deep damage to the permafrost and caused fires in regions that really, as far as we can tell, have never burned before, right? And so to put it in simple language, the world is not only much hotter, but there is much more energy, solar energy, being trapped in our environment, right? And in the uh, the overall atmosphere of the Earth. And the result is that all of these weather patterns are being accelerated. The heat is also captured in the oceans, which therefore transmit greater energy to the atmosphere. It's not evenly distributed. And as you've probably seen in the news reports, people are really coming into focus on the fact that the most extreme weather change, the most extreme temperature increase seems to be concentrated in the Arctic region. This is obviously highly problematic for our capacity to retain the ice caps or to prevent massive movements of glaciers into the oceans, which will ultimately reduce both the albedo effect at the poles and dramatically increase sea level around the world. And so the evidence is all around us that this is happening. We understand the science of it very well, and I don't want to completely reproduce stuff that I've already discussed with you, but I will very quickly return to the idea that there is a delicate energy balance between the Earth's atmosphere and the solar energy that it absorbs on an annual basis. And that especially for the last 10,000 years, but really going back practically a million years, the Earth has been in an equilibrium in which the radiation absorbed has, let me put it differently, the radiation that reaches the Earth is absorbed and reflected in a ratio that allows the Earth to stay in a relatively narrow temperature band. And the fact that we've been in this temperature band that has been very stable for 10,000 years, but relatively stable for a million years, has allowed the kind of biological life that currently characterizes the Earth to flourish. And what we are doing in terms of removing carbon and other material from the surface of the Earth, and again, I'm coming to understand more about this the more I read about it, that the carbon that is stored in the Earth's surface in the form of coal and oil was deposited there 3 million plus years ago at a period in which there was actually less oxygen in the Earth's atmosphere. And so it was harder for carbon dioxide to form. And so vegetable and animal matter, as opposed to decaying and releasing in carbon dioxide, sunk and was fossilized. And there's a wonderful phrase in one of the books I'm reading about this: sunshine underground. It's as if the coal and the oil and the other fossil fuels store hundreds of thousands of years of the radiation that the Earth absorbed from the sun underground sunshine, as opposed to the normal sunlight we get. And for the last 200 years, we have been unearthing all of that fossil fuel and consuming it, burning it to create our own energy, right? And that energy has allowed us to completely transform our civilization, to explode in terms of the population of human beings on the planet, to have this period of incredible technological development, urbanization, and agricultural revolution, lifespans lasting twice as long, a much more in terms of health, in terms of education, in terms of resources consumed, nutrition, etc., a much higher level of quality of life or well-being for so many billions more human beings, right? And so we are the beneficiaries of this, but the cost of this has been, as these fuels have been used and consumed to produce goods and energy and facilities and infrastructure for us, their gases have been released into the atmosphere. Those gases trap heat, and the result is that we are now disrupting this delicate equilibrium, and it is beginning to manifest in terms of the kinds of weather events that we're encountering. And I will just very briefly point out to you some of the evidence. I know this is familiar at this point, right? And so as you can see, right, for 3 million years, the temperature on Earth, based again on both observations, and the observations you can see, that's the black line, at most go back 2 million years, right? The good observations go back 1 million years. And again, ice core goes back about 1 million years. Fossilized trees we can carbon date to later than that. Some of the sediment on the bottom of the ocean lets us go back a similar length of time. And so we can correlate our simulations with the actual data. The correlation is a good match, and so that gives us confidence in the further back periods. But all of this to say, as best we can tell, we've never really gone out of this band, but we do believe that we are headed rapidly out of this band, that we already have baked in 1.5 degrees of global warming in what we have already emitted, right? And to be as clear as possible, we're up to about 1.1 degrees Celsius that has already occurred. So another 0.4 degrees gets us up to that 1.5 measure. But most people who study this think that we will be very, very fortunate if we don't change very rapidly to avoid 2.5, 3 degrees. And once we get above 2, we're going into periods that we haven't encountered for millions of years. Looking at a shorter time frame, we have this geological time period called the Holocene. Literally, it means the period of warmth, right? The epoch of warmth. And this goes back about 10,000 years. And it's worthwhile noting, right, just how stable the temperature has been in this period and how nicely warm it has been. And I'll contrast this with the instability of previous epochs in a little while. But one of the things that anthropologists and others note is that it's around 10,000 years ago, maybe more like 8,000 years ago, when we got used to the temperature being stable, that human agriculture, human urban civilization began to develop. With it, then eventually written language and what we view as culture or civilization, and that we are now leaving this band of warmth, right? This is why geologists now call this the Anthropocene, right? Our activity is fundamentally altering the earth processes, and that's most obvious in the temperature and the surface of the earth. And so we are seeing more energy, more heat, more drought, more fire, more monsoon as a result. If we look at this in the long term, again, right, going back a million years and looking at the carbon dioxide in the atmosphere, we have pushed the carbon dioxide, and please note that this diagram is now somewhat out of date. We're up higher than 380 parts per million carbon dioxide in the atmosphere. And the temperature has not risen to completely catch up. It lags, but we should expect the temperature also to come out of these bands characteristic of the last million years. This is going to be a disaster for human beings, a disaster for coral reefs, a disaster for animals and plants. Some of the stuff we've talked about before, I'm just trying to refresh your memory that in particular, if we keep it at 1.5 degrees, basically what we've already put into the atmosphere, we still put 14% of the world's population at risk of extreme heat on a regular basis. But if we go up that extra half degrees, it goes up to more than a third of the population. And as you can see, coral reefs mostly disappear. Large portions of the animals and plants of the earth lose large portions of their range. I know you've seen this diagram too many times, but it's still impossible to fully make sense of. The basic idea here is that we can't treat the processes that we are unleashing through our emissions as isolated. They are interacting, and as they interact, they also tend to reinforce each other. We burn fossil fuel, it increases the atmospheric concentration of greenhouse gases. This increases temperature. This then leads to Arctic ice melting, and that then leads to things like subsea frozen solid methane being released, and that then increases methane in the atmosphere, which causes a further rise in temperature, and round we go, right? So let me just point to, right, the Arctic ice caps, right? This diagram shows the previous extent and the current extent, and in the Arctic and the Antarctic, we're already seeing substantial loss, maybe as much as 10% of the ice at the poles. Forest lost, and in particular, we're concerned about tropical rainforests, which are so important to both the carbon and the humidity cycles of the earth, the melting of the permafrost, the dying of the coral reefs, the destruction of topsoil, the way in which this represents a threat to really important interconnected planetary systems, and puts us in the terrain of global catastrophic risk, a terrain we have never been in before and seem poorly equipped to think about. That's just showing you a little bit more of the detail of the Arctic sea ice decrease. You can see it graphically as well from 1979 to 2022. It goes up and down based on the winter-summer cycling, but what you can see is a steady decline overall. We see something similar in the Antarctic areas that used to be covered in ice in 40 years ago, 30 years ago, even 10 years ago. Those ice shelves have now collapsed. The just stunning decline in the acreage of tropical rainforests. And in particular, right, we've talked together before about the albedo effect, the reflection that the ice on the poles shoots or bounces solar energy back out into the solar system, so it doesn't stay on the Earth. We could also talk about the fact, right, that the Amazon has this tremendous capacity to absorb carbon dioxide out of the atmosphere. It is losing that capacity as it turns from forest to savanna, and the process often involves the rainforest burning. And as the rainforest burns, that carbon dioxide that it stores is then released. To um, summarize this, one simple way to put this is that for most of the last 150 years, the period of intensive industrial development and the energy intensive and hence fossil fuel dependent era of capitalism that we've lived through, the full extent of our greenhouse gas emissions has not actually gone into the atmosphere and hence contributed to climate change in the way that it could have. Because although we have been emitting an awful lot, it's also the case that the land, the trees, the biomass, and the oceans have been drinking a lot of it up for us so it doesn't go into the atmosphere. And it appears that these sinks for our emissions are now at the saturation point, or actually being undermined in their capacity to sink carbon dioxide by climate change. So I now want to turn to some of the science, and I want to introduce a framework, and some of you may have seen this is both a book, Breaking Boundaries, that's written by Johan Rockström, who is a Swedish climate scientist, but the director of the Potsdam Institute for Climate Impact Research, which is obviously in Germany, and then Will Steffen, who is an American, a chemist, but interested in the chemistry of climate change, and who worked at the Australian National University. And Stefan and Rockström, along with a whole bunch of other scientists, but they are the most important originators of this framework of thinking about planetary boundaries. And I would point out to you the book, which Rockström wrote with another planet scientist, Alan Gaffney, is quite readable. And not only that, there is also now a Netflix series which presents this with good graphics and again in a lay fashion to make it intelligible. But the basic idea, and this goes back to research that was done by James Lovelock in the 1980s and 1990s on the idea of a Gaia system, an Earth-wide ecosystem. And Lovelock was more speculative about this idea, that it appears that although we tend to think of individual ecosystems on the planet Earth, there may be interlocking relationships between the ecosystems such that you are best served to think of the planet as a whole, as a single ecosystem. And what Stefan and Rockström have done is to really take that intuition or that speculation from Lovelock and turn it into a much more concrete, specific, detailed model of what they call Earth systems. And there are 9 of them. I'll go into the details of this in a moment. 9 of them that are interlocking or that connect to each other. So let me just give a little bit of the basic elements of this planetary boundary framework so you have a sense of it. The first big idea is that there are Earth systems, right? And I'll throw out there to illustrate the nitrogen system, right? And so on a planetary scale, the chemical, the element nitrogen circulates, right? And it is interesting because it's not an airborne molecule. It mainly stays in the land and in biological life, and then in water, in streams, lakes, oceans, and it is perpetually being circulated in a way that regulates its balance in different ecosystems and contributes to life on the planet, and that we are getting to the point where we can understand the various interconnecting Earth systems, and then can begin to think through as concretely as possible what are their boundaries, meaning at what point might their ability to regulate themselves or equilibrate be disrupted. And to be as clear as possible, this is not about climate change alone, right? The nitrogen system is being disrupted by human activity, but the human activity that is disrupting it is not necessarily the same activity that generates climate change, or at least it's a different system we're interfering with by manufacturing nitrogen to serve as fertilizer. We are putting higher concentrations in the soil and in ultimately the water. It ends up in the ocean, and it is creating real problems for marine life that's independent from climate change. But as we begin to disrupt the ecosystems of the oceans, that may have implications for climate change. This is hence the idea that these Earth systems are interconnected or interlocking systems. So the idea that there are boundaries and then tipping points for large scale discontinuities, that within a range, these Earth systems are able to regulate themselves. We discussed this with regards to climate change just a few minutes ago, right? That for much of the industrial period, we didn't actually suffer the damage that the extent of our emissions would have caused because forests grew more rapidly. Different forms of phytoplankton and marine life absorbed more of the carbon, right? And so there's a sense that these systems can regulate themselves, equilibrate themselves up to a point. Once you cross that boundary or tipping point, then the system loses its capacity to regulate itself. And then in a sense, all bets are off, right? This is the idea of large scale discontinuities, that once you cross that boundary, it's no longer going to be able to regulate itself. And then you really don't know what's going to happen on a planetary scale. So this allows Rockstrom and Stefan to model the capacity of the Earth and its systems to regulate and correct for variability on a planetary scale. The idea here is a self-controlling system, and one of the examples they use is that we go through glacial and interglacial periods, cycles of ice ages, and then warmer periods, and that seems to be self-correcting, right? The ice never completely covers the planet. The ice never completely melts away. It progresses and recedes on a cyclical basis, where processes unleashed by the ice ages tend to end the ice ages. Processes released by the contracting of the ice tend to start a new ice age. So this is the system of the capacity of the Earth to create self-regulating, self-controlling systems. But the risk is that human perturbations, right? Sorry, that's their scientific language, will destabilize these Earth systems at a planetary scale. So let me get a little bit more concrete. And I find this diagram to be extremely important and extremely illuminating. What this diagram shows is that from 1850 to 2010, humanity released a tremendous amount of fossil fuel into the atmosphere and really disrupted land use and changed, therefore, the capacity of the plants of the earth to absorb this carbon dioxide. But that over the same period, the ocean, the forests absorbed large quantities of that carbon dioxide so that they did not actually end up in the atmosphere at higher concentrations than they had been there for the pre-industrial period until around the 1970s, right? And that ever since then, the concentrations in the atmosphere have been growing, in part because we have exhausted the capacity of the forest and the oceans to continue to bail us out, to correct for the excess carbon dioxide, methane, et cetera, that we're putting in the atmosphere. That for over 100 years, we didn't get outside the range of carbon, methane, etc., that the planet could handle, correct for, re-equilibrate. But now we have crossed that boundary, right? And what they suggest, what Stefan and Rostrom suggest, is that this is actually only one of 9 processes. And so you can see when it comes to climate change, right, this is the safe operating range. We are now out of that range. But when it comes to other processes, we are perhaps even further out of the range than we are with regards to climate change. And so some of this has to do with the rate of extinction and the loss of biological diversity. Some of this has to do with the way in which we're using land and deforestation, paving over asphalt, etc. Some of this has to do with, for instance, introducing plastics into the genomes and ecosystems of the earth. Some of it has to do with nitrogen and phosphates and biochemical flows. Some of it has to do with our use of water. We managed to get ozone depletion under control. This is a success, right? We are still in the safe zone here. They don't fully understand, and I think this is really important. It's what distinguishes them from Lovelock and earlier speculative accounts. They say we just don't understand certain of these phenomena, and some of the boundaries have not been crossed yet. And so this is, I think, then played out in terms of the very precise metrics that the framework of planetary boundaries gives us to, on the one hand, say, what is the boundary value for climate change? Let's call it 350 parts per million carbon. Has it been crossed? Yes, we're up at 412 now. What was the pre-industrial value? And is it getting worse, right? Comparing 2011 with 2021. And as you can see, you can do this in every metric. So as opposed to merely being able to say human beings are threatening the planet, we can now say in which Earth system are we threatening, to what degree, and what is the trend line. And so it gives us much greater precision to be as clear as possible. Some countries, Germany and New Zealand stand out, are actually using this framework to determine their national environmental policies. So they are asking in each of these 9 metrics. Are our current practices sustainable? Are our contributions to the biodiversity loss or the production of anthropogenic nitrogen and phosphorus unsustainable? If so, what would a sustainable target be? Germany, which has become most advanced at this, is requiring each of its federal states to create a decade-long plan to bring its nitrogen, its phosphorus, its greenhouse gas emissions down to a sustainable level, right? And so this framework gives us a much more concrete way of thinking through the ways in which we are damaging the planet. Among other things, it shows how these processes are connected to each other through global feedback mechanisms. Some of these processes are more localized. Some of them are not at all localized, right? And we can think of, right, the nitrogen cycle as being relatively localized. It pollutes the water in a particular region, whereas greenhouse gases, once they get into the atmosphere, they go everywhere. They tend to be dispersed and ultimately to produce a uniform concentration. The idea of interconnected global processes is best understood and best illustrated through the idea of the tipping points in global climate change, with Arctic sea ice being extremely important in terms of being connected to both the circulation in the Atlantic Ocean of water, that deep currents that tend to moderate temperature that have been slowing down since the 1950s, being related also to ice cover in Greenland and Iceland, and then boreal forests in North America, Amazon rainforest in South America, even being connected to accelerating ice loss in the Antarctic at the opposite pole of the planet. And so this idea that these are Earth systems, what distinguishes them is the fact that they ultimately are interconnected across the entire surface of our spherical planet. One of the things that has been a consequence of this framework and the greater precision in measurement that it's introduced is that as time has gone by, the degree of climate change required to trigger crises has gone down and down, right? This is what this diagram shows. In 2001, we thought maybe that there wouldn't be high threats to the various biological systems until the temperature reached maybe 3 or 4 degrees Celsius higher. We now think that it's potentially as low as 2 or even 1.5 degrees Celsius. And so you can see across the board in various studies that temperature of danger keeps decreasing to the point where we are very close to it already. By the way, it's not just environmental scientists who are paying attention to this. The World Economic Forum is also paying attention to it. Their single most dangerous risk in terms of its likelihood and its impact is climate action failure, right? So we can see again that the payoff of this framework in terms of being able to graph where phosphorus cycle interruption, nitrogen cycle interruption, land change use, and fresh water are all at risk on the planet today. Let me go to the last thing I really want to talk with you about today. And this is the idea of the great derangement. So I keep bombarding you with evidence that climate change is deeply dangerous to us. And by the way, it's not only climate change. Why aren't we changing more quickly? Why did it take us a year and a half to get very modest legislation passed? Why are farmers in the Amazon still burning their forests, right? Why are we still using these chemical processes to extract nitrogen? And I find a whole range of literature to be extremely important here. I will point very quickly to Amitav Ghosh, the great derangement I've already mentioned. He is a novelist, a very accomplished Indian of Bengali extraction novelist, but he's been writing about climate change. His uh, the area he comes from, Bengal, is deeply threatened by climate change. His more recent book, The Nutmeg's Curse, continues the exploration of this. But also other scientists, other philosophers, other theorists, I think, are very useful in understanding the limits of our culture. So Timothy Morton, who's a philosopher, his concept of hyperobjects that we just can't get our heads around the nature of the processes because they are so large, so ubiquitous, so threatening. Donna Haraway at UC Santa Cruz suggesting that we really need to return to a way of thinking about nature as being part of our kinship network. William Cronin, a historian at the University of Chicago, who's done really interesting work on the evolving understanding of nature in the last couple hundred years in the United States. Charles Taylor, who I've talked with you about before, who has suggested that we have completely disenchanted the world, taken away any understanding of any sort of meaning or divine inhering in nature itself. So let me synthesize very quickly for you some of what this body of literature suggests. And its overall suggestion is that we've lost our capacity to fully fathom nature's depths and dangers, and that this is a product of the scientific revolution, urban existence, modern agriculture, and the overall human mastery of nature, which is really a quite recent, quite novel phenomenon. And the idea that we take for granted that we are not threatened by nature, it's not necessary to be in awe of and intimidated by, and also grateful for nature, is really quite recent, most 100 years old, and that it really alienates us from the cultural resources for relating to nature that have been characteristic of most of human civilization. So very quickly, in terms of a superficial archaeology of how our culture changed so quickly, one aspect of this would be the disenchantment of the world, right? And the move into what Charles Taylor calls an immanent frame, a frame in which we are simply part of a natural world that does not transcend us, that does not contain forces that are larger and deeper and more meaningful than we are, that we've got to relate to and show respect for. And Taylor, and he's following in the terrain developed by people like Nietzsche and Max Weber, suggests this is simultaneously the work of Protestantism or religious ideas that suggest, no, God is not in and of the world, but external to the world. The world was created by him, but created by God for us to master, and God has essentially abandoned the day-to-day operation of the world to the operation of the laws of nature, which science better understands than theology, right? And so this idea that as we developed more and more advanced scientific understandings, science actually proved much more powerful than religion in controlling a completely meaningless but law governed nature. And so this has changed our understanding of nature. This leads to an idea of nature as governed by laws and predictable and masterable, right? And the mastery of nature is not just a theoretic possibility in science, it is a technological reality, which is the precondition for so much of the modern world, right? And so Ghosh in The Great Derangement talks about what it's like to live in Bangladesh, to live in an area where tigers are a constant threat, and the way in which this gives you a certain fear, but also a certain appreciation for the majesty of nature, for the fact that it is not something that can be controlled. And he points out, right, Amitav Ghosh now lives in New York, has lived there for 20 years, that this is not an experience that you have in Manhattan or most of the urban world in which the majority of human beings now live. We've also changed our built environment, right? And so air conditioning and heat would be a simple example. It really doesn't matter what the temperature is outside. We are comfortable inside. Similarly, our economy. We don't, for the most part, at least in the developed world, need to be terribly attuned to what's going on in our atmosphere or our current seasons, whether there's a short summer, a late spring, a drought. We get to pull up to the grocery store, pull up to the restaurant, and the food that we need is there, right? And so we're distant from the processes, the natural processes on which we rely, because of what our energy system and what our modern civilization allow us to take for granted. A fifth aspect of this, and again, I think it's phenomenal to think through, right? We have literally more than doubled the average lifespan of a human being. Malnutrition is much less threatening to almost every human being on the planet. That doesn't mean that there aren't 20% of us that are food insecure, 20% of the human beings on the planet, or perhaps a larger portion of that. But the constant threat of hunger that was characteristic of human life for the vast majority of human existence on the planet is no longer the threat that it was for the majority of human beings on the world today. Progress has been real, but is progress inexorable? Is it something that more or less automatically proceeds and that we should just simply take for granted? And again, this body of thinkers says the last 150 years have led us to be far too sanguine, far too optimistic about a one-directional track, right? And the evidence is around us that progress may have been a short episode of recent human history coming to an end. Materialism, the idea that the essential well-being of human beings progresses, as does the extent of their consumption of material resources. Again, another deep assumption of recent culture, which may be impairing our ability to deal with cultural and environmental change. Structural roots, and here I'll be very brief, that these ideas don't just come to us from culture as a free-floating autonomous realm, but are rooted in deep structural forces in modern society. Capitalism, colonialism, globalization have all given a strong material impulse to these cultural changes. And the conclusions here, I think, are really important. We have deprived ourselves of the cultural and imaginative resources necessary to comprehend and cope with an unmasterable nature, especially in the Anthropocene, as we have disrupted its equilibrium. That we have to beware of totalizing explanations. It's not all about cultural change, but it is time to start thinking about where we can go to gain the cultural resources, the categories, the concepts, the ways of thinking and imagining we need. And that may be turning to non-Western and indigenous cultures or dissident modern subcultures like the Romantics and the Transcendentalists. Let me just conclude for today by pointing you again to this diagram, which shows you how much we've been protected by natural processes from our own destructive behavior. But I also want to share with you this diagram. And this is a diagram of the last 100,000 years of weather as we can reconstruct it based on, this is actually Greenland ice cores, and just see how for the last 10,000 years, nature has, in a sense, cooperated with us, has been very moderate in its temperature change, and has kept us in this wonderful Goldilocks warm zone. And that for the previous 90,000 years, there were these sharp up and down temperature changes, and that everything that we see seems to indicate we are pushing nature back out of the stable temperate band that it's been in. And what we should expect is that we will see a much less stable temperate climate going into the future. Can we prepare ourselves for that? Can we do our best to mitigate the processes we're unleashing to stop before it's too late in order to reach that conclusion, in order to generate the will, the consensus, the energy necessary to tackle this problem? We're going to probably have to revive our understanding of nature. I should say, revise our understanding of nature and our place in it. And that involves deep cultural work that we seem to be ill-equipped to do at the moment.